Hi, I'm Lars Ruthotto. I'm an associate professor at Emory in the departments of math and computer science, and my research tries to understand machine learning, and specifically deep learning, from a mathematical perspective. You guys have all heard about deep learning, I think, in the news, and you know this technology is all around us. So for example, when you do an image search online, you will be blown away by the number of images you get. And how does this work? So the technology behind this is deep learning. See, see this picture here of a dog, probably that's what we would say. And there's a deep neural network that classifies and assigns really precise labels to images it finds on the web. How does this exactly go? So this image is taken and fed into something called a deep network. You see one example here, one tiny example here. And that network is very powerful and very generic and has previously seen millions of other images like those ones and uses this experience to assign a label. In this case, the correct answer for what's on the picture is a commodore. So the really specific dog breed that the networks have been able to recognize. However, we almost don't, or oftentimes we don't know how deep learning actually works and makes decisions. There are many mathematical problems and computational problems that my research group is addressing. Deep learning is a specific subfield of machine learning and AI. Oftentimes these terms are used interchangeably, but it sort of is good to know what we are in for. So in deep learning, you have a deep neural network, and they are typically depicted as you see here on the right. There are some inputs, then there are some outputs, and the stuff in between, most people call them the hidden features, and you're not supposed to look at them, but one of my research themes is actually to really look into what's going on in between and model that through math. Specifically, what we are doing is we model this through differential equations. And one example to give you up front and to put maybe to expose the math here. So say you have training data. So these are just points in, let's call them X in R2, and they are labeled with two colors, red and blue, for the two different classes. And now what we want to do is we want to learn a function. So this is a function that basically maps X. So it maps X to either 0 or 1 for all X, so that we can learn the underlying mechanism to classify this data. To do that, we use a DNN, and one thing that we do very special in my group is that this part here, we don't model it as a black box as is common, but we use something called ODEs, ordinary differential equations, to model that process. We have an input X, and we take that X and make it the initial state of a differential equation. And then the mapping that we are learning is how to advance this point. So we basically have a d dt of y at time t is equal to some f. That is a neural network that depends on some weights, let's call them theta, of y of t. And there are a couple of nice things that happen when you do that, because then basically this is the input of the network, and y at some terminal time is the output. And once you do that, you can study what is going on in the deep network through differential equations. So all this part here is a differential equation. You can design differential equations that are giving you nice properties computationally or theoretically. And you can really help make deep learning much more predictable that way. In this case here, we could even play how these points are moving around in the space as a video, which is super cool. And you can find many of these online because these ideas have really sparked a lot of research in the community. One particular result is that in the end, machine learning is driven by optimization, because you always need to fit a model to data by minimizing a loss function. And it's been noted that the loss function in general in deep learning is really ugly. So you see this function here, and the optimization problem now is to sort of go through this landscape and hopefully ending up in this global minimizer here. And it can be really easy to be stuck someplace. So once you not used. So this is for a normal neural network. So this is like a normal network. Once you do these differential equation, once you bring in differential equations, this is how the loss function looks like. So here it's a very smooth process, and it's going to be very easy to find the minimizer and fit your data. Yeah, so basically that's the key thing my group has been doing, is crack open this black box of deep neural networks, bring in more math, and make it much more easier to understand, more computationally efficient, and also hopefully more reliable, because there are really big issues with deep learning. And yeah, thanks for watching, and hopefully you learned something.